Right now, at this very moment, something extraordinary is happening in the depths of our solar system. 3I Atlas, the massive interstellar visitor that has puzzled astronomers for months, is accelerating toward the Sun, not by choice, not by propulsion, but by the inexorable pull of gravity that governs everything in our cosmic neighborhood. The numbers tell a story of relentless approach. As of October 29th, 2025, the object sits approximately 1.9 astronomical units from our star. That translates to roughly 176 million kilometers, a distance that shrinks with every passing hour. The orbital mechanics are straightforward physics. The closer 3I Atlas gets to the Sun, the faster it moves, pulled by gravitational forces that increase with proximity. Current velocity measurements show the object traveling at nearly 40 kilometers per second relative to the Sun. To put that in perspective, imagine crossing the entire United States in less than 2 minutes. This speed continues climbing as the visitor falls deeper into the solar gravity well, following a hyperbolic trajectory that will carry it around our star and back toward interstellar space. Astronomers tracking the approach have calculated perihelion, the point of closest solar approach, with remarkable precision. The trajectory models, refined through months of observations from over 200 observatories worldwide, predict the critical moment will arrive in late November 2025. At that point, 3I Atlas will pass the Sun at a distance closer than Earth's orbit, experiencing solar heating unlike anything it has felt during its million-year journey through the cold darkness between stars. But here is where the approach becomes more than just orbital mechanics. As 3I Atlas moves sunward, it enters a zone where solar radiation intensifies exponentially. Every day brings stronger heating. Every hour means more energy absorbed by the nucleus surface. The ices that have remained frozen for eons are beginning to respond. Temperature gradients across the object's surface are shifting dramatically. The sunward-facing hemisphere now experiences conditions capable of sublimating water ice, the volatile that dominates most comet compositions. Deeper within the nucleus, heat slowly conducts inward, a thermal wave penetrating layers that have known only the absolute cold of interstellar space. This is not a gradual, gentle warming. The physics of solar heating creates dramatic temperature differences between day and night sides of the rotating nucleus. Surface temperatures on the sun-facing hemisphere may already exceed 200 degrees Kelvin, warm enough to turn solid ice directly into vapor. Meanwhile, the night side remains at temperatures barely above absolute zero. The countdown has entered its critical phase. In roughly 50 days, 3I Atlas will reach perihelion. 50 days for temperatures to climb. 50 days for activity to intensify. 50 days until we discover whether this silent giant will finally reveal its true nature, or whether it will maintain its enigmatic behavior right through the moment of greatest solar heating. The approach has begun. The transformation is inevitable. What happens next will rewrite our understanding of interstellar visitors. Telescopes around the world are registering something remarkable. 3I Atlas is getting brighter, and the change is happening faster than anyone expected. Photometric measurements collected over the past 3 weeks show a clear upward trend in the object's apparent magnitude. This is not simply the result of getting closer to Earth. The distance factor has been carefully removed from the calculations. What remains is intrinsic brightening. real physical changes in how much light the object produces and reflects. On October 1st, 2025, 3I Atlas measured at apparent magnitude 14.2, barely visible to amateur telescopes with modest apertures. By October 15th, it had brightened to 13.7. Now, as of October 29th, measurements show magnitude 13.1. That represents more than a full magnitude increase in less than a month, meaning the object appears roughly 2.5 times brighter than it did 4 weeks ago. The physics behind this surge tells us exactly what is happening on that distant nucleus. As solar heating intensifies, ice sublimation rates are climbing exponentially. More ice turning to gas means more molecules escaping into space. More escaping gas means more sunlight scattered by the expanding coma. The brightening directly traces increasing activity levels. Ground-based observatories, equipped with sensitive CCD cameras, are capturing this transformation night after night. The data streams into central databases where analysts track brightness changes across multiple wavelengths. Visible light shows the strongest increase, but infrared observations reveal even more dramatic changes as thermal emission from warmed dust particles adds to the overall signal. What makes this brightening particularly significant is its rate of change. The steepness of the brightness curve suggests sublimation processes are accelerating faster than models predicted. Either the surface area of active regions is expanding as new patches of ice become exposed, or the sublimation efficiency is higher than theoretical calculations assumed. Temperature is the driving force behind everything we are observing. Solar flux at 3. I-Atlas's current distance delivers roughly 270 watts per square meter to the sunward hemisphere. That may not sound like much compared to the 1,360 watts per square meter that Earth receives, but it is more than sufficient to drive vigorous ice sublimation. The relationship between solar distance and brightness follows well-established physical laws. As the object moves closer to the sun, heating increases according to the inverse square law. Half the distance means 4 times the solar flux. This creates a feedback loop where approaching closer increases heating, which increases activity, which increases brightness, allowing better observations, which reveal even more detail about the ongoing transformation. Amateur astronomers with backyard telescopes are beginning to pick up 3I Atlas in their eyepieces now. What required professional equipment just weeks ago has become accessible to dedicated observers with good dark skies and patience. The celestial visitor is literally emerging from obscurity. But the surge poses a question astronomers are urgently trying to answer. If brightness continues climbing at this rate, what will peak activity look like at perihelion? The projections are staggering. Something invisible is growing around 3I Atlas, and only infrared eyes can see its true scale. The coma, that tenuous atmosphere of gas and dust surrounding the nucleus, has transformed from a modest envelope into a vast structure that dwarfs planets. Spherex Space Telescope observations from late October 2025 reveal a carbon dioxide cloud extending more than 500,000 kilometers from the central nucleus. That is roughly 1.3 times the distance between Earth and the Moon. This is not the coma we saw 3 months ago. When JWST first observed 3I Atlas in early August, the extended atmosphere measured perhaps 200,000 kilometers across. Now, it has more than doubled in size, and the expansion shows no signs of slowing. Every day adds thousands of kilometers to the outer boundary as freshly sublimated molecules stream away from the warming nucleus. Hubble Space Telescope captures the visible portion of this awakening in stunning detail. Images taken on October 27th show a bright central condensation surrounded by a diffuse glow that extends across the entire field of view. The innermost coma, dominated by dust particles that scatter sunlight efficiently, has developed intricate structure. Shells and arcs appear in the brightness distribution, suggesting episodic bursts of activity as different regions of the nucleus rotate into sunlight. The composition of this expanding atmosphere reveals the progressive heating of 3I Atlas. Carbon dioxide, which sublimates at extremely low temperatures, dominates the outer coma regions. This gas began escaping months ago, when the object was still far from the sun, cold enough that water remained frozen solid. Now, as temperatures climb, water vapor joins the outflow in increasing quantities. Ground-based spectroscopy measures the velocities of escaping molecules. Gas streams away from the nucleus at speeds approaching 500 meters per second, fast enough to overcome the weak gravitational pull of the relatively small solid core. These velocity measurements feed directly into calculations of gas production rates, which have climbed to nearly 200 kilograms per second as of late October. To visualize that production rate, imagine a fully loaded washing machine worth of ice turning to gas and escaping into space every 5 seconds. Hour after hour, day after day, the nucleus hemorrhages mass as solar heating drives relentless sublimation. Over the course of a single day, 3I Atlas loses roughly 17 million kilograms of material. Yet given its estimated total mass of 33 trillion kilograms, this mass loss barely registers as a fraction of the whole. The dust component of the coma adds another dimension to the awakening. Particles lifted off the nucleus by escaping gas scatter sunlight across a broad range of wavelengths. Polarimetry measurements suggest dust grain sizes ranging from submicron particles to chunks several millimeters across. The larger particles follow ballistic trajectories, creating the curved structures visible in Hubble images as they slowly spiral outward under the combined influence of gravity and radiation pressure. The coma is no longer dormant. It breathes, expands, and evolves with each passing day. This is an interstellar visitor coming fully alive. The numbers refuse to cooperate, and astronomers are running out of explanations. 3I Atlas is now producing gas at unprecedented rates. The coma extends 500,000 kilometers into space. Dust streams away in visible jets. Every measurement confirms vigorous comet activity. Yet, the one signature that should accompany all this outgassing remains stubbornly absent. The non-gravitational acceleration is still essentially zero. Updated astrometry, compiled through October 29, 2025, incorporates over 5,000 positional measurements from more than 300 observatories worldwide. The data quality has never been better. Measurement precision reaches sub-arc-second accuracy. Statistical analysis accounts for every possible source of systematic error. The orbital solution is rock solid, and it shows pure gravitational motion. The upper limit on non-gravitational acceleration sits below 12 meters per day squared, slightly tighter than measurements from 3 months ago, despite dramatically increased activity levels. In practical terms, this means 3I Atlas follows a trajectory determined entirely by the Sun's gravity and its initial velocity vector. the jets of gas escaping at hundreds of meters per second, carrying momentum that should push the nucleus in the opposite direction, appear to have no measurable effect whatsoever. This is deeply wrong. The physics of rocket propulsion is not optional. When mass leaves an object in one direction, conservation of momentum demands the object recoils in the opposite direction. Comets have displayed this behavior for as long as humans have measured their orbits precisely. Non-gravitational forces show up as systematic deviations from purely gravitational trajectories, tiny but detectable drifts that accumulate over months of observation. To Borisov, the previous interstellar comet discovered in 2019 showed exactly the expected behavior. Its non-gravitational acceleration matched predictions based on visible gas production. The orbital deflection made perfect sense given its size and activity level. It behaved like a textbook example of comet physics in action. 3. I-Atlas breaks the textbook. The paradox has intensified rather than resolved as more data accumulates. Every new measurement confirms what should be impossible. Active outgassing without orbital response implies mass so enormous that the recoil becomes undetectable. But mass estimates based on that assumption push toward values that challenge everything astronomers understand about interstellar debris populations. Some researchers propose that gas escapes preferentially in directions that cancel out overall momentum transfer. Perhaps jets fire in opposing pairs, creating thrust that balances perfectly. But imaging observations show no such symmetry. The visible jets emerge from discrete active regions, without obvious counterparts on the opposite hemisphere. Others suggest the dust-to-gas ratio might be far higher than assumed, with heavy dust particles carrying away momentum more efficiently than theoretical models predict. Yet, spectroscopic measurements of gas production rates and photometric observations of dust brightness both seem inconsistent with this explanation. The most uncomfortable possibility remains the simplest. 3. I-Atlas is genuinely, extraordinarily massive. The 33 trillion kilogram estimate, which seemed extreme when first calculated months ago, may actually be conservative. The object could weigh even more, a true giant among interstellar visitors, shrugging off its own breath like a mountain ignoring wind. The velocity paradox deepens with every observation. Activity climbs, while acceleration remains frozen at zero. Something fundamental is missing from our understanding. Understanding what is happening to 3I Atlas requires understanding heat, and the Sun is a remarkably efficient furnace even at great distances. Solar radiation operates through electromagnetic waves that travel through space at the speed of light. These waves carry energy that gets absorbed when they strike solid surfaces. The amount of energy delivered depends on distance according to a simple but powerful relationship called the inverse square law. Move twice as far from the Sun and you receive 1/4 the energy. Move half the distance and energy increases fourfold. At 3, I-Atlas's current position of roughly 1.9 astronomical units from the Sun, the solar flux measures approximately 270 watts per square meter on surfaces facing directly toward our star. That may seem modest compared to the 1,360 watts per square meter bathing Earth, but it represents a dramatic increase from the mere whisper of energy the object experienced during its journey through interstellar space. The transformation begins at the surface. Sunlight strikes the dark, ice-rich nucleus and converts from electromagnetic radiation into heat. Surface temperatures climb until sublimation begins, the process where solid ice transforms directly into gas without passing through a liquid phase. This is not melting. There is no water pooling on 3I Atlas. The vacuum of space and low pressures make liquid phases impossible. Different ices sublimate at different temperatures. Carbon dioxide ice, which dominates the outer layers based on spectroscopic observations, becomes active around 150 degrees Kelvin. That is still brutally cold by Earth standards, roughly minus 123 degrees Celsius, but warm enough in the airless environment of space to drive vigorous sublimation. Water ice requires higher temperatures, becoming active around 200 degrees Kelvin. The heating is not uniform. 3I Atlas rotates, though the exact period remains uncertain. As different regions rotate into sunlight, they warm rapidly. When rotation carries them back into shadow, they cool just as quickly. This creates dramatic thermal cycles that stress the nucleus structure. Ices expand and contract. Dust layers insulate underlying material. Cracks may form and propagate as thermal stresses build. Heat also conducts inward from the surface, though this process happens slowly. Ice is a poor thermal conductor, so the warming wave penetrates only meters or tens of meters into the nucleus over the course of weeks. Deeper material remains at the frigid temperatures of interstellar space, unaware that the surface kilometers above is transforming. This creates chemical layering in the outgassing. Surface ices sublimate first. As those layers erode away, deeper material gets exposed. If the nucleus formed through accretion of material at different times or temperatures, each layer might have distinct composition. The progressive heating peels back these layers like an onion, revealing formation history through changing chemistry. The Sun is rewriting 3I Atlas from the outside in, transforming an interstellar iceberg into an active comet. The physics is straightforward. The implications remain profound. The chemistry is changing, and James Webb Space Telescope is watching it happen in real time. New spectroscopic observations, conducted in late October 2025, reveal something remarkable. Water vapor, which appeared only as weak signatures in earlier measurements, now blazes prominently across multiple infrared wavelengths. The relative abundance of water compared to carbon dioxide has shifted dramatically over just 6 weeks of observation. This is the volatile cascade, a progressive activation of different ice species as solar heating penetrates deeper into the nucleus structure. Carbon dioxide sublimated first months ago when 3I Atlas was still far from the Sun, and surface temperatures barely reached 150 degrees Kelvin. That early outgassing created the extended coma detected by SphereX and dominated the chemistry through summer and early autumn. Now, water joins the mix in force. Surface temperatures across sun-facing regions have climbed past 200 degrees Kelvin, the threshold where water ice sublimation becomes vigorous. The spectroscopic signature is unmistakable. Emission lines at 2.7 microns and 6.3 microns indicate water molecules vibrating and rotating as they stream away from the warming nucleus at hundreds of meters per second. But water and carbon dioxide are not the only players. JWST's high-resolution spectrograph detects carbon monoxide strengthening in recent observations. This volatile requires even higher temperatures than water to sublimate efficiently from pure ice, suggesting that surface layers are warming beyond 250 degrees Kelvin in some locations. The sun-facing hemisphere during local noon may be experiencing temperatures that would feel merely chilly rather than impossibly cold. Trace species add complexity to this unfolding chemical story. Methane appears as faint absorption features. Ammonia shows tentative signatures that require confirmation from additional observations. Formaldehyde, that simple organic molecule important for prebiotic chemistry, emerges in spectral regions previously dominated by noise. Each new molecule tells us something about where and how 3I Atlas formed. The carbon dioxide abundance suggests birth in the frigid outer reaches of its parent stellar system, beyond the snowline where carbon dioxide freezes alongside water. The presence of carbon monoxide indicates even colder formation regions, or mixing with material from the diffuse interstellar medium during the long journey between stars. The organic molecules hint at chemical processing that occurred either in the protoplanetary disk where 3I Atlas originated, or during exposure to cosmic rays over millions of years in interstellar space. Radiation can drive chemical reactions even in frozen ices, building complex molecules from simpler starting materials. Every organic compound detected represents a window into chemistry operating under conditions utterly unlike Earth. Ground-based spectroscopy complements the space-based observations. Very large telescope measurements track how emission line strengths vary with time, revealing day-night cycles as the rotating nucleus brings different regions into view. Gemini Observatory observations map the spatial distribution of different volatiles within the coma, showing where water-rich gas separates from carbon dioxide-rich regions. The cascade continues accelerating. As 3I Atlas moves closer to the Sun, temperatures will climb higher. Deeper layers will sublimate. New chemistry will emerge. The object is peeling itself, apart molecule by molecule, revealing its alien composition. Chapter 7. The Nickel Mystery deepens. The chemical anomaly that puzzled astronomers in August has become even stranger as 3I Atlas approaches the Sun. Very large telescope observations from late October 2025 show nickel emission lines blazing brighter than ever across multiple wavelengths in the 700 to 900 nanometer range. The signal strength has increased by more than a factor of 3 compared to measurements taken just 2 months earlier. Every new spectrum confirms the presence of abundant nickel atoms streaming away from the nucleus in the expanding coma. Iron remains absent. This selective appearance defies basic expectations about how metals behave in cometary environments. In nearly every astronomical context, nickel and iron appear together. They form from similar nucleosynthetic processes in dying stars. They often exist in the same minerals and alloys in meteorites and rocky bodies. Finding one without the other is like discovering a forest where every tree is oak, but maple trees are completely missing from regions where both should thrive. The mystery deepens with the production rate calculations. Spectroscopic analysis indicates 3I Atlas releases approximately 2 grams of nickel per second into its coma. That may sound modest, but integrated over days and weeks, the cumulative amount becomes substantial. Over a month, the object sheds more than 5,000 kilograms of nickel. Where is all this metal coming from, and why is iron not following the same release mechanism? Temperature dependence provides one crucial clue. The nickel emission strength follows a steep power law relationship with heliocentric distance. As 3I Atlas moves closer to the Sun and surface temperatures rise, nickel production increases dramatically. The scaling suggests a threshold effect, some critical temperature where the release mechanism suddenly becomes efficient. New theoretical papers propose several mechanisms that might explain selective nickel release. Photodesorption, driven by solar ultraviolet radiation, could break chemical bonds in surface compounds, liberating nickel atoms while leaving iron locked in more stable molecular structures. Laboratory experiments recreating low-temperature, low-pressure conditions similar to comet surfaces show that certain organometallic compounds preferentially release nickel when exposed to ultraviolet light. Another possibility involves the thermolysis of metal carbonyls, compounds where metal atoms bond to carbon monoxide molecules. Nickel carbonyl decomposes at lower temperatures than iron carbonyl, potentially explaining why one metal appears while the other remains hidden. If 3I Atlas contains unusual concentrations of these exotic compounds, the chemistry could produce exactly the observed pattern. The spatial distribution of nickel emission within the coma adds another dimension to the puzzle. High-resolution spectroscopy reveals that nickel concentrations peak near the nucleus and decline gradually with distance. This suggests ongoing production from the solid surface, rather than delayed release from dust grains traveling outward. Whatever mechanism liberates nickel operates directly on nucleus material. Some researchers point to the carbon dioxide-rich composition as a potential connection. Extreme cold during formation might have allowed unusual metal-bearing ices or minerals to condense, compounds that simply do not form in the warmer environments where typical solar system comets originate. 3I Atlas may carry chemistry that reflects truly alien formation conditions. The nickel mystery remains unsolved, but every new observation constrains possible explanations. The answer lies somewhere in the intersection of unusual chemistry and exotic formation environments. The dust surrounding 3I Atlas is not behaving like ordinary comet dust, and polarimetry measurements are revealing why. Observations conducted through late October 2025 using specialized filters that measure polarized light show something unexpected in the scattered sunlight. The polarization fraction, which indicates how light waves align after bouncing off dust particles, reaches values significantly higher than typical for solar system comets at similar distances from the Sun. This tells us the dust grains have unusual properties. Particle size distribution analysis suggests 3I Atlas produces an abnormally high proportion of small grains, particles measuring less than 1 micron across. These tiny fragments scatter light very efficiently, but carry little mass. Larger grains, chunks measuring millimeters or more, appear less abundant than models predict based on the total dust brightness. The size distribution is skewed toward the small end compared to what astronomers normally observe. This matters because grain size determines how dust behaves after leaving the nucleus. Small particles feel radiation pressure from sunlight more strongly than gravity. They accelerate away rapidly, pushed by photon impacts into expanding trajectories that carry them far from the nucleus. Large particles, less affected by radiation pressure, follow more ballistic paths, dominated by the weak gravitational pull of the nucleus and the momentum imparted by escaping gas. The dust-to-gas ratio provides another piece of the transformation puzzle. Current estimates suggest 3I Atlas produces roughly equal masses of dust and gas, a ratio near unity. Most active comets show ratios ranging from 0.1 to 10, with considerable variation depending on composition and activity level. A ratio near 1 places 3I Atlas in the middle of the observed range, neither unusually dust-poor nor dust-rich. Yet the total dust production rate has climbed dramatically as solar heating intensifies. Late October measurements indicate approximately 180 kilograms of dust escaping per second, comparable to the gas production rate. This represents a doubling from measurements taken in early September. More surface area has become active, or existing active regions have increased their output as temperatures rise. Color measurements across multiple wavelengths reveal that 3I Atlas dust appears slightly redder than typical solar system comet dust. The reddish tint suggests the presence of complex organic compounds, carbon-rich molecules that absorb blue light preferentially and reflect red wavelengths more efficiently. These organics may coat mineral grains or exist as separate organic-rich particles. The dust composition connects directly to formation environment. Red, organic-rich dust indicates carbon chemistry operated during the object's birth, either in its parent protoplanetary disk or through subsequent processing by cosmic rays. The exact mix of minerals and organics will remain uncertain until direct sampling occurs, if such an opportunity ever arises. Thermal emission from dust particles adds infrared brightness to the visible scattered light. As grains absorb sunlight and warm, they radiate in the infrared. Spitzer-class observations show thermal emission consistent with dust temperatures around 250 degrees Kelvin, slightly cooler than the nucleus surface, but warmer than surrounding gas. The dust transforms solar radiation into heat, creating a warm envelope around the frozen core. Hidden within the spectrum of 3I Atlas lies information that reaches back billions of years to the moment of its formation, written in the language of isotopes. High-resolution spectroscopy, conducted during late October 2025, has achieved something remarkable. By analyzing the precise wavelengths of molecular emission lines with extreme accuracy, astronomers can distinguish between molecules containing different isotopes of the same element. Water made with normal hydrogen looks slightly different from water containing deuterium, hydrogen's heavier cousin with an extra neutron in its nucleus. The deuterium to hydrogen ratio in 3I Atlas. Water vapor measures approximately 150 parts per million. This means that for every million hydrogen atoms, roughly 150 are actually deuterium. That ratio carries profound implications because it directly traces the temperature conditions during ice formation billions of years ago. Deuterium enrichment happens preferentially at low temperatures. When water ice condenses from gas in cold environments, molecules containing the heavier deuterium atom freeze out slightly more efficiently than normal water. The colder the environment, the stronger this preference becomes. The ratio measured in 3I Atlas water suggests formation temperatures below 30 degrees Kelvin, far colder than the regions where most solar system comets formed. Carbon isotopes tell a complementary story. The ratio of carbon-13 to carbon-12 in carbon monoxide molecules shows values consistent with interstellar medium abundances, rather than the slightly different ratios typical of solar system material. This suggests 3I Atlas either formed from relatively unprocessed material, similar to the diffuse interstellar gas, or spent enough time exposed to cosmic rays during its journey, that isotopic ratios equilibrated toward interstellar values. Oxygen isotopes add another layer to this chemical archaeology. 3 separate isotopes exist naturally: oxygen 16, 17, and 18. Their relative abundances depend on nuclear processes in stars and subsequent chemical processing in protoplanetary disks. Preliminary measurements suggest oxygen isotope ratios in 3I Atlas. Carbon dioxide differ slightly from terrestrial values, though the uncertainties remain large enough that confirmation requires additional observations. Nitrogen isotopes in cyanogen molecules show tentative evidence for enrichment in nitrogen 15 compared to typical solar system ratios. If confirmed, this would indicate chemical processing in very cold conditions, or inheritance from pre-solar grains, microscopic particles that existed before our solar system formed and preserved isotopic signatures from other stellar environments. These isotopic fingerprints collectively paint a picture of formation in an environment quite unlike the region where Earth and the inner solar system took shape. 3I Atlas carries chemical memory of a different stellar system's outer reaches, places where temperatures barely rose above the background radiation of space itself. The object is a frozen library preserving information about stellar chemistry operating under extreme conditions. Every isotope ratio narrows the possibilities for where and how this interstellar visitor originated. The measurements remain preliminary and uncertainties are substantial, but the emerging picture suggests 3I Atlas formed in truly frigid conditions at the edge of its parent system, then wandered through interstellar space for millions or billions of years before gravity brought it into our cosmic neighborhood. The fingerprints endure, waiting to reveal their secrets. The spectrum reveals molecules that should not surprise us, yet somehow they do. 3I Atlas carries organic chemistry from another stellar system, and we are reading its molecular signature for the first time. James Webb Space Telescope observations from late October 2025 detect formaldehyde clearly in the infrared spectrum. This simple organic molecule, composed of carbon, hydrogen, and oxygen, appears as distinct absorption features at 3.6 microns. The detection confirms that carbon chemistry operated during 3I Atlas formation, building molecules more complex than simple carbon monoxide or carbon dioxide. Methanol joins the organic inventory, with tentative signatures acquiring confirmation from additional observations. If verified, methanol presence would indicate that hydrogen addition reactions occurred. Processes where hydrogen atoms attach to carbon monoxide on cold grain surfaces to build progressively more complex molecules. This chemistry happens efficiently in the frigid environments of molecular clouds and outer protoplanetary disk regions. Hydrogen cyanide shows stronger signals than earlier observations detected. This molecule, poisonous to Earth life, but crucial for prebiotic chemistry, forms readily in environments where carbon and nitrogen chemistry intersect. Its presence alongside formaldehyde and methanol suggests 3I Atlas contains a suite of simple organics that could serve as building blocks for more complex chemistry. Acetylene appears in the spectrum as well, a hydrocarbon indicating that pure carbon-hydrogen chemistry operated alongside oxygen-bearing organic synthesis. The mix of different organic families, oxygen-rich molecules like formaldehyde and methanol, alongside hydrocarbons like acetylene, points toward diverse chemical pathways operating simultaneously or sequentially during formation. More complex organics remain beyond current detection limits. Amino acids, if present, exist in concentrations too low for remote spectroscopy to identify. Similarly, the long-chain carbon molecules that give some solar system comets their dark surfaces would be invisible to current observations. Direct sampling would be required to inventory the full complexity of organic chemistry locked within 3I Atlas ice. The organic abundance appears comparable to that of solar system comets, based on the relative strengths of organic versus water emission features. This suggests that carbon chemistry operates similarly across different stellar systems, producing comparable molecular inventories when similar physical conditions prevail. The chemistry may be alien in origin, but follows universal physical laws. These molecules formed billions of years ago in a protoplanetary disk orbiting a star we will never see. They survived ejection from that system, millions of years drifting through interstellar space, exposed to cosmic radiation, and now sublimate under solar heating as 3I Atlas makes its close approach to our Sun. Each molecule represents continuity across cosmic distances and timescales that dwarf human experience. The organic inventory matters beyond pure chemistry. These molecules connect to fundamental questions about how common life-relevant chemistry is throughout the galaxy. If organic synthesis operates efficiently in many stellar systems, producing similar molecular suites, then the chemical preconditions for life may be widespread. 3I Atlas carries not just ice and rock, but information about galactic-scale chemical evolution. The molecules continue streaming into space, gradually depleting the reservoir built up over billions of years. We are witnessing the dismantling of alien organic chemistry in real time. Something visually wrong is happening in the sky, and it is getting more pronounced with each passing week. Hubble Space. Telescope images from late October 2025 show the sunward glow that puzzled observers back in July has evolved into a dramatic feature that dominates the inner coma structure. The anti-tail, that apparent projection of material pointing toward the sun rather than away from it, now extends more than 50,000 kilometers in the forward direction. This is not a subtle effect requiring careful image processing to reveal. It blazes clearly in raw telescope data. The physics behind anti-tails involves perspective geometry and dust grain dynamics that create optical illusions, but calling this an illusion undersells how strange it appears. When you look at 3I Atlas through a telescope, your eye tells you that material is flowing sunward. Every instinct trained by observing normal comets rebels against the image. Tails should point away from the sun, swept outward by solar wind and radiation pressure. This tail defies that expectation. Forward scattering provides the most likely explanation. Dust particles of specific sizes scatter sunlight preferentially in the forward direction, toward the observer rather than away from the light source. When Earth's viewing geometry aligns properly with the Sun-Comet-Earth angle, these forward-scattered photons create brightness enhancements that appear to project toward the Sun. The particles themselves still move outward, carried by radiation pressure and their initial velocity from the nucleus. Only the light creates the illusion of sunward motion, but models struggle to fully reproduce the observed brightness distribution. The anti-tail shows structure, bright regions and dark lanes that suggest real physical variations in dust density rather than simple geometric effects. Some regions of the nucleus may be producing dust with different size distributions than others, creating the complex patterns visible in high-resolution images. Ground-based observations using adaptive optic systems confirm what Hubble sees from space. Multiple observatories image the anti-tail structure from different viewing angles as Earth's rotation changes perspective throughout the night. The feature persists across all viewing geometries during late October, suggesting it represents genuine physical structure rather than fleeting atmospheric effects or instrumental artifacts. The temporal evolution adds another dimension to the mystery. Time series imaging shows the anti-tail brightness fluctuating on timescales of hours to days. These variations likely trace changing dust production rates as different active regions on the rotating nucleus point toward Earth. When a particularly productive jet rotates into view, the forward scattered light intensifies. When that region rotates away, brightness declines. Polarization measurements indicate the dust producing the anti-tail has properties consistent with small particles, grains, measuring less than 1 micron across. These tiny fragments scatter light according to my scattering theory, which predicts strong forward scattering for particles comparable in size to visible light wavelengths. The anti-tail refuses to conform to simple explanations. It represents a complex interplay of grain properties, viewing geometry, and dust production patterns that pushes observational astronomy toward its limits. We see the effect clearly. Understanding it completely remains elusive. The nucleus is no longer uniformly active. Discrete jets have emerged, and they are changing the appearance of 3I Atlas dramatically. High-resolution imaging from late October 2025 reveals at least 4 distinct jet structures emanating from specific points on the nucleus surface. These are not the diffuse, uniform outflow that characterized earlier observations. These are focused streams of gas and dust, narrow columns that extend tens of thousands of kilometers before dispersing into the broader coma. The jets appear brightest near the nucleus, where dust concentrations remain highest. As material streams outward, the jets gradually fade and widen, mixing with the ambient coma environment. But within the innermost few thousand kilometers, the collimated structure remains clearly defined, visible as bright streaks against the darker background sky. Rotational modulation provides the smoking gun evidence for localized active regions. Photometric measurements, tracking brightness variations over time, show periodic oscillations with an amplitude of roughly 30%. The brightness peaks every 11.3 hours, suggesting this represents the rotation period of the nucleus. As active regions rotate into view facing Earth, brightness increases. When those regions rotate away, brightness declines. The rotation rate itself carries information about the nucleus structure. An 11.3-hour period is neither unusually fast nor slow for a comet-sized object. It suggests the nucleus maintains sufficient structural integrity to rotate as a coherent body, rather than tumbling chaotically or fragmenting under centrifugal forces. For an object potentially 5 kilometers across, this rotation rate creates surface velocities of roughly 40 centimeters per second at the equator, fast enough to be dynamically interesting, but not fast enough to threaten structural stability. Spectroscopic mapping reveals that different jets carry slightly different chemical compositions. One jet shows enhanced water vapor relative to carbon dioxide. Another appears richer in carbon monoxide. These variations suggest the jets tap into subsurface reservoirs with different ice mixtures, perhaps reflecting chemical layering that developed during initial formation or subsequent processing. The jet orientations provide constraints on the nucleus spin axis direction. By measuring where jets emerge and how they sweep across the sky as the nucleus rotates, astronomers can triangulate the orientation of the rotation pole. Preliminary analysis suggests the spin axis tilts significantly relative to the orbital plane, creating strong seasonal effects where different hemispheres receive vastly different solar heating throughout the rotation cycle. Temperature differences drive the jet activity. Sunlit regions heat rapidly, driving vigorous sublimation that creates high gas pressures beneath thin surface dust layers. When pressure builds sufficiently, the overlying material ruptures, allowing gas to escape in focused jets rather than diffuse seepage. The jets represent the nucleus releasing pent-up pressure through weak points in its crust. New jets may activate as 3. I-Atlas continues approaching the Sun. Regions currently dormant could burst into activity when solar heating reaches critical thresholds. The nucleus is awakening region by region, revealing its structure through the pattern of emerging jets. The transformation from dormant iceberg to active jetting comet continues accelerating with each passing day. Behind 3 I-Atlas, stretching back along its orbital path, like breadcrumbs marking a cosmic journey, lies a trail of dust particles that refuses to behave according to standard models. Wide-field imaging conducted during late October 2025 reveals the extended dust trail now spans more than 2 million kilometers along the object's trajectory. This represents material ejected weeks and months ago that has gradually separated from the nucleus under the combined influence of solar radiation pressure, orbital mechanics, and the initial velocities imparted during ejection. The trail should be symmetric, with dust distributed evenly along the orbital path, both ahead of and behind the nucleus. Physics dictates that particles ejected with similar velocities and similar radiation pressure properties should spread symmetrically as they follow slightly different orbits around the Sun. Yet, observations show a distinct asymmetry. More dust appears to lag behind the nucleus than leads ahead of it. This preferential trailing suggests something about either the ejection process or the particle properties that current models do not fully capture. One possibility involves the timing of dust production. If 3 I-Atlas produces more dust when certain active regions face specific directions relative to its orbital motion, particles could receive preferential velocities that favor trailing distributions. Imagine a rotating garden sprinkler where most water shoots backward relative to the direction of travel. Another explanation focuses on particle size evolution. Small dust grains feel radiation pressure more strongly than large particles. If the dust trail contains a population of fragmenting grains that break apart over time, the size distribution evolves as particles age. Older particles behind the nucleus might be smaller on average than younger particles near the nucleus, creating brightness asymmetries that appear as density variations. The color of the dust trail provides additional clues. Photometric measurements across multiple wavelengths show the trail appears slightly redder than the inner coma. This color difference suggests either chemical changes in the dust as it ages under solar radiation exposure, or preferential loss of bluer particles that get pushed away more efficiently by radiation pressure. Gravitational effects also sculpt the dust trail geometry. Particles ejected from the nucleus do not escape entirely. They enter slightly different orbits around the Sun, some with higher energy that carry them farther from our star, others with lower energy that keep them closer. This orbital diversity stretches the dust cloud along the orbital path, creating the extended trail visible in wide-field images. Computer simulations attempting to reproduce the observed trail geometry require careful tuning of multiple parameters, including ejection velocities, size distributions, and the timing of dust production. No single simple model matches observations perfectly. The trail represents an integration of complex processes operating over weeks of active outgassing. Future observations will track how the trail evolves as 3I Atlas continues toward perihelion. Does the asymmetry grow stronger or fade? Do new structures emerge as activity intensifies? The dust trail is not just debris. It is a record of everything 3I Atlas has experienced during its solar system passage, written in particles floating through space. The cloud of gas and dust surrounding 3I Atlas is not spherical, and the distortions reveal forces sculpting the coma into complex three-dimensional structures. Multi-wavelength observations from late October 2025 show pronounced asymmetries in how different gas species distribute themselves around the nucleus. Water vapor concentrates preferentially on the sunward side, where temperatures drive the most vigorous sublimation. Carbon dioxide, which sublimates at lower temperatures, shows a more symmetric distribution, but still displays enhancement in sun-facing regions. The asymmetry becomes even more dramatic in dust distribution. Imaging reveals a fan-shaped structure extending primarily in the sunward direction, with much less material visible in the anti-solar hemisphere. This is not what simple physics would predict. Radiation pressure from sunlight should push dust away from the sun, creating enhancement in the tail region opposite the sun. Instead, we see the reverse. Solar wind pressure provides part of the explanation. The stream of charged particles flowing outward from the sun at hundreds of kilometers per second creates a dynamic pressure that compresses the sunward side of the coma. Gas and dust get pushed back toward the nucleus on the sun-facing hemisphere, creating a bow shock-like structure similar to what happens when supersonic flow encounters an obstacle. But solar wind alone cannot explain the full complexity of observed asymmetries. The nucleus jets, those discrete streams of material emerging from active regions, inject gas and dust with specific directional velocities. If jets preferentially point in certain directions relative to the sun, they create intrinsic asymmetries in the coma before any external forces act. Three-dimensional modeling attempts to reconstruct the coma structure from two-dimensional telescope images. This inverse problem requires assumptions about how material flows and where observers view the structure from. Different viewing angles can create dramatically different projected appearances of the same three-dimensional distribution. What appears as a sunward enhancement from Earth's perspective might actually represent a more complex structure tilted relative to the Sun-Earth line. Spectroscopic velocity measurements add crucial constraints to these geometric reconstructions. By measuring Doppler shifts in emission lines from different parts of the coma, astronomers can determine whether material moves toward or away from Earth. Gas approaching shows blue-shifted spectral lines. Receding gas shows redshifted lines. Mapping these velocities across the coma reveals the three-dimensional flow pattern. Current measurements indicate expansion velocities vary significantly across different coma regions. Material near the jets moves faster than gas in quiescent areas. The sunward coma shows compression signatures where outflowing gas encounters solar wind pressure. The anti-solar tail displays acceleration as particles escape the nucleus' gravitational influence, and radiation pressure takes over. The asymmetries also evolve with time as the nucleus rotates and different jets activate. Time-lapse imaging spanning several rotation periods shows the coma brightness distribution shifting and pulsing. What appears as a static structure in single images actually represents a dynamic, constantly changing environment. Understanding these asymmetries requires combining observations across multiple wavelengths, multiple viewing angles, and multiple time snapshots. The coma is not a simple expanding sphere. It is a complex hydrodynamic structure shaped by competing forces and geometric effects. Every astronomer watching 3I Atlas knows the question lurking beneath every observation. Will it hold together, or will thermal stress tear the nucleus apart before perihelion? History provides sobering precedent. Comet Linear fragmented spectacularly in 2000, disintegrating into dozens of pieces as solar heating exceeded the structural strength holding its nucleus together. Comet Elenin broke apart in 2011 while still far from the Sun, destroyed by stresses that seemed modest compared to what perihelion passage usually delivers. Comet Ison vaporized during its extremely close solar approach in 2013, torn apart by tidal forces and thermal shock. 3. IATLAS faces similar dangers, though its apparent enormous mass might provide protection that smaller comets lack. Larger objects have higher structural strength simply due to their size. The gravitational self-attraction of a 5-kilometer nucleus, while weak by planetary standards, still provides meaningful cohesion. More mass means more gravity, holding the pieces together against disruptive forces. Monitoring for fragmentation requires vigilant observation of multiple indicators. The most obvious sign would be sudden brightness changes as new surface area becomes exposed when the nucleus splits. Fragmentation events typically produce dramatic brightening as fresh ice sublimates rapidly from newly exposed interior material. Observers watch the light curve obsessively, looking for unexpected surges that might signal structural failure. Changes in rotational period provide another diagnostic. If the nucleus fragments, the pieces typically spin faster than the parent body due to conservation of angular momentum. Careful timing of brightness variations could reveal period changes, indicating that breakup has occurred. So far, through late October 2025, the 11.3-hour rotation period remains stable within measurement uncertainties. Spectroscopic monitoring tracks whether new chemical signatures appear suddenly. If fragmentation exposes interior layers with different composition than the surface, the spectrum should show abrupt changes in relative abundances of different volatiles. The chemistry has evolved gradually as solar heating penetrates deeper, but no sudden compositional shifts have occurred that might indicate catastrophic structural failure. The jets themselves might provide early warning. If thermal stress creates fractures propagating through the nucleus interior, gas pressure could find new escape routes, creating additional jets from previously inactive regions. Alternatively, existing jets might shut down, if fractures disrupt subsurface pathways that channel gas to active regions. Any unexpected changes in jet patterns warrant close attention. Thermal stress modelling calculates the forces acting on the nucleus as temperature gradients create differential expansion. Ice expands when warmed. Rock and dust have different thermal expansion coefficients than ice. These mismatches create internal stresses that can exceed the tensile strength of weak comet material. Models suggest that stresses peak not at perihelion, but during the rapid warming phase leading up to closest approach, exactly the period 3I Atlas is entering now. The object has survived this long. It endured the initial warming that activated carbon dioxide sublimation months ago. It withstood the onset of water ice activity that began in recent weeks. But the most severe test still lies ahead as temperatures continue climbing toward perihelion values. The fragmentation watch continues around the clock. Behind every observation of 3I Atlas lies an unprecedented coordination effort spanning continents, time zones, and international borders. More than 350 observatories now contribute data to the global tracking campaign as of late October 2025. This represents an increase of over 100 facilities since the initial discovery in July. The network has grown organically as word spread through astronomical communities about the unusual nature of this interstellar visitor. Professional observatories, university telescopes, and serious amateur installations have all joined the effort. The logistics are staggering. As Earth rotates, different observatory sites rotate into darkness and gain access to the night sky. Coordinating observations requires careful scheduling to ensure continuous coverage as 3I Atlas moves across different sky regions, visible from different longitudes. When European telescopes lose the object to dawn twilight, observatories in North America take over. As sunrise ends American observations, facilities in Australia and Asia begin their viewing sessions. Data flows into central repositories managed by the Minor Planet Center and European Space Agency coordination networks. Raw positional measurements arrive continuously, sometimes hundreds per night during periods of good weather and favorable viewing geometry. Analysts compile these positions into updated orbital solutions, refining trajectory predictions and checking for any unexpected deviations from purely gravitational motion. Photometric data requires different handling. Brightness measurements come in various formats from different instruments, each with its own calibration standards and filter systems. Standardization protocols convert diverse measurements into common magnitude scales, allowing meaningful comparison. Teams track how brightness changes with time, building light curves that reveal rotation periods and activity variations. Spectroscopic observations present the most complex coordination challenges. Allocating telescope time on major facilities requires months of advanced planning through competitive proposal processes. Observing windows are precious, measured in hours rather than days. When atmospheric conditions at one observatory turn unfavorable, backup plans shift observations to alternative facilities if possible. The goal is maximizing spectral coverage across as many wavelengths as possible. Space-based assets add another coordination layer. Hubble space telescope observations require scheduling weeks in advance through a system that balances 3I Atlas against hundreds of other astronomical targets competing for limited time. James Webb Space Telescope faces similar pressures, with observing programs planned months ahead. Getting these premier facilities pointed at 3I Atlas during critical activity phases requires both advanced planning and flexibility to accommodate unexpected developments. Communication happens through multiple channels. Professional astronomers use email lists, online platforms, and coordination websites to share observing plans and preliminary results. Telegram groups and Slack channels enable real-time coordination during active observing campaigns. Conference calls scheduled to accommodate multiple time zones allow teams to discuss strategy and results. Amateur astronomers contribute crucial observations that fill temporal gaps between professional telescope sessions. Their smaller instruments cannot match the light-gathering power of research telescopes, but their availability and dedication provide high-cadence monitoring that would be impossible with large facilities alone. Many amateurs have decades of experience and produce data quality rivaling professional observations. This global effort represents astronomy at its collaborative best, bringing together diverse resources and expertise focused on understanding a single object that will never pass this way again. In just 4 days, 3I Atlas will pass within 30 million kilometers of Mars, and spacecraft orbiting the red planet are preparing for a unique observation opportunity. The encounter on November 3rd, 2025, represents something extraordinary in the history of interstellar object astronomy. For the first time, humanity will observe such a visitor from 2 completely different vantage points simultaneously. Earth-based telescopes provide one perspective. Mars orbiters offer another, separated by the distance between the 2 planets. European Space Agency's Mars Express and Trace Gas Orbiter have received updated commands to point their cameras toward the approaching object during the flyby window. The observations will be challenging. Even at closest approach, 3I Atlas remains tens of millions of kilometers from Mars, far beyond the optimal range for cameras designed to image surface features measured in meters. But the different viewing geometry makes the attempt worthwhile. NASA's MAVEN orbiter, primarily focused on studying Martian atmospheric escape, has been cleared to participate in the campaign. While its instruments were not designed for deep space observations, any data collected will complement Earth-based measurements and provide constraints on the object's brightness and activity that cannot be obtained from terrestrial viewpoints alone. The geometry creates advantages that go beyond simple distance differences. Mars sits roughly 90 degrees away from Earth, relative to 3I Atlas during the encounter period. This means Mars-based instruments view the object from a dramatically different angle, seeing portions of the coma and nucleus surface that remain hidden from Earth's perspective. The sunward coma, compressed by solar wind pressure and partially obscured from Earth's view, should be more visible from Mars' position. Phase angle effects represent another scientific opportunity. The phase angle, the Sun Object Observer angle, determines how sunlight reflects off dust particles and how shadows fall across surface features. Mars observations will capture 3I Atlas at phase angles, impossible from Earth during this time period. Comparing brightness at different phase angles constrains dust particle properties and surface roughness. Timing the observations requires precise coordination, accounting for light travel time between planets. Commands uploaded to Mars orbiters must specify exactly when to point instruments toward predicted positions of 3I Atlas. Any errors in trajectory predictions could result in cameras pointing at empty space while the object passes through adjacent sky regions. data return will not be instantaneous. Radio signals carrying observational data from Mars to Earth take approximately 13 minutes to traverse the distance between planets during the encounter period. Images and measurements collected on November 3rd may not arrive at ground stations until hours later, depending on communication window schedules and data transmission rates. The scientific value extends beyond pretty pictures. Multi-vantage photometry helps resolve ambiguities in coma structure and activity distribution that single viewpoint observations cannot address. Different viewing angles reveal whether brightness features represent real physical structures or geometric projection effects. Weather on Mars poses no concern. The orbiters operate above the thin Martian atmosphere, immune to the clouds and dust storms that affect surface operations. They will have clear views, assuming the spacecraft and instruments function nominally. In 4 days, humanity gets its first stereoscopic view of an interstellar visitor, while Earth-based telescopes will lose sight of 3I Atlas behind solar glare during perihelion passage. One spacecraft will maintain its watch from the perfect vantage point. Parker Solar Probe, humanity's closest envoy to the Sun, follows an orbit that brings it within just a few million kilometers of our star multiple times per year. This extreme proximity normally focuses its instruments on solar wind physics and coronal structure. But in late November 2025, Parker will be positioned to observe 3I Atlas from the solar side, the one perspective completely unavailable to Earth-based observers. The WSPR camera, short for Wide Field Imager for Parker Solar Probe, was designed to photograph the solar corona and track structures in the solar wind. Its wide field of view covers large swaths of sky around the Sun, perfect for monitoring comets passing through the inner solar system. WSPR has already observed dozens of sun-grazing comets, those unfortunate visitors that pass so close to our star, they often vaporize completely. 3I Atlas will not approach nearly that close. Its perihelion distance keeps it safely beyond the most extreme solar heating. But from Parker's perspective, near the Sun, the comet will appear well separated from the bright solar disk, observable without the overwhelming glare that blinds Earth-based instruments during this critical period. The observation window opens in late November and extends through early December as Parker completes another close solar pass. During this time, WSPR will capture images every few hours, building a time-lapse sequence showing how 3I Atlas behaves during its moment of maximum solar heating. These observations will reveal whether activity surges to predicted levels, whether the nucleus fragments under thermal stress, or whether something unexpected occurs. One crucial question Parker might answer involves the anti-tail structure. From Earth, we see this feature as a sunward-pointing projection. From Parker's solar vantage, the geometry reverses. What appears as forward-pointing structure from Earth should appear as a tail extending away from the Sun when viewed from Parker's position. If WSPR sees something different, that would indicate the anti-tail involves more complex physics than simple forward-scattering geometry. The solar-wind interaction represents another observation priority. Parker's instruments measure solar wind density, velocity, and magnetic field strength directly. Comparing these measurements with 3I Atlas's coma behavior observed by WSPR will show how the comet responds to changing solar wind conditions. Does the coma compress when dense solar wind regions pass? Do magnetic structures deflect around the obstacle created by outgassing? Data transmission from Parker poses challenges. the spacecraft must survive extreme temperatures near the Sun using a sophisticated heat shield. It collects data during close passes, but transmits that data to Earth only when farther from the Sun, where communication becomes easier. Whisper observations of 3I Atlas perihelion passage may not reach Earth until days or weeks after the actual event. The wait will be worth it. Parker Solar Probe will provide the only direct observations of 3I Atlas during the most dynamic phase of its solar system visit, capturing data from a vantage point no other observatory can match. James Webb Space Telescope is preparing for its most detailed look yet at 3I Atlas, and the observation plan reads like a masterclass in infrared spectroscopy. The scheduled observations for early November 2025 will employ multiple instruments simultaneously to capture data across a wide range of infrared wavelengths. NIR-SPEC, the near-infrared spectrograph, will target molecular emission lines from water, carbon dioxide, carbon monoxide, and organic compounds. MIRI, the mid-infrared instrument, will map thermal emission from dust particles and search for signatures of complex organic molecules that emit at longer wavelengths. This deep dive aims to answer specific questions that earlier observations could not address. What is the exact deuterium to hydrogen ratio in water vapor? Are there amino acids present in detectable quantities? Does the dust contain crystalline ice or amorphous ice structures? Can we identify specific organic compounds beyond the simple molecules already detected? The exposure times will be substantial, measured in hours rather than minutes. JWST will stare at 3I Atlas long enough to collect photons from faint spectral features that require exceptional signal-to-noise ratios to distinguish from background noise. This extended integration time means sacrificing observations of other targets, a trade-off that reflects the scientific priority assigned to this unique interstellar visitor. Spatial resolution represents another advantage JWST brings to the campaign. The telescope can distinguish structures within the inner coma that appear blurred together in ground-based observations. Mapping how different molecules distribute themselves around the nucleus will reveal whether various ices sublimate from the same active regions or from distinct locations with different compositions. Thermal mapping will show temperature variations across the nucleus surface with unprecedented precision. Sunlit regions should glow bright in infrared wavelengths, while shadowed areas remain cold. The temperature distribution constrains thermal models that predict how heat conducts into subsurface layers and drives the observed outgassing. The observations must be scheduled carefully around other JWST commitments. The telescope operates as an international facility with observation time allocated through competitive proposals from astronomers worldwide. Getting extended time for 3I Atlas required demonstrating that the science return justifies displacing other worthy programs. Data processing will begin immediately after observations complete. Raw detector images contain instrumental signatures that must be removed through calibration pipelines before scientific analysis can proceed. Within days of observation, preliminary results should emerge, showing whether the deep dive revealed new surprises or confirmed existing understanding. The deepest infrared look at an interstellar visitor ever attempted is about to begin. James Webb Space Telescope is preparing for its most detailed look yet at 3I Atlas, and the observation plan reads like a masterclass in infrared spectroscopy. The scheduled observations for early November 2025 will employ multiple instruments simultaneously to capture data across a wide range of infrared wavelengths. NIR-SPEC, the near-infrared spectrograph, will target molecular emission lines from water, carbon dioxide, carbon monoxide, and organic compounds. MIRI, the mid-infrared instrument, will map thermal emission from dust particles and search for signatures of complex organic molecules that emit at longer wavelengths. This deep dive aims to answer specific questions that earlier observations could not address. What is the exact deuterium to hydrogen ratio in water vapor? Are there amino acids present in detectable quantities? Does the dust contain crystalline ice or amorphous ice structures? Can we identify specific organic compounds beyond the simple molecules already detected? The exposure times will be substantial, measured in hours rather than minutes. JWST will stare at 3i Atlas long enough to collect photons from faint spectral features that require exceptional signal-to-noise ratios to distinguish from background noise. This extended integration time means sacrificing observations of other targets, a trade-off that reflects the scientific priority assigned to this unique interstellar visitor. Spatial resolution represents another advantage JWST brings to the campaign. The telescope can distinguish structures within the inner coma that appear blurred together in ground-based observations. Mapping how different molecules distribute themselves around the nucleus will reveal whether various ices sublimate from the same active regions or from distinct locations with different compositions. Thermal mapping will show temperature variations across the nucleus surface with unprecedented precision. Sunlit regions should glow bright in infrared wavelengths, while shadowed areas remain cold. The temperature distribution constrains thermal models that predict how heat conducts into subsurface layers and drives the observed outgassing. The observations must be scheduled carefully around other JWST commitments. The telescope operates as an international facility with observation time allocated through competitive proposals from astronomers worldwide. Getting extended time for 3i Atlas required demonstrating that the science return justifies displacing other worthy programs. Data processing will begin immediately after observations complete. Raw detector images contain instrumental signatures that must be removed through calibration pipelines before scientific analysis can proceed. Within days of observation, preliminary results should emerge showing whether the deep dive revealed new surprises or confirmed existing understanding. The deepest infrared look at an interstellar visitor ever attempted is about to begin. While professional observatories command the headlines, a quiet revolution is happening in backyard observatories around the world, where dedicated amateur astronomers are making crucial contributions to 3i Atlas science. Hundreds of amateur observers now track the interstellar visitor nightly, weather permitting. Their telescopes range from modest 8-inch instruments to serious half-meter aperture systems that rival small professional facilities. What they lack in light-gathering power compared to research telescopes, they compensate for with availability and dedication. Professional telescopes are scheduled months in advance and allocated by competitive proposals. Amateur telescopes point wherever their owners choose, whenever clear skies permit. This flexibility provides something professional astronomy struggles to achieve: high-cadence monitoring. An amateur astronomer can image 3i Atlas every clear night for hours at a stretch, building dense time series data that reveals short-term variations invisible to surveys that observe once per week. Brightness fluctuations on timescales of hours, sudden changes in coma structure, or unexpected activity bursts all become detectable with this intensive coverage. The photometry proves particularly valuable. Measuring brightness through standard filters and comparing those measurements against calibrated reference stars produces light curves that trace activity evolution. When compiled from dozens of observers across different continents, these measurements provide nearly continuous brightness monitoring as Earth rotates. Gaps in professional telescope coverage disappear when amateur data fills the intervals. Online coordination platforms enable real-time data sharing and collaboration. Observers upload their images and measurements to central databases where analysts compile results and identify interesting features requiring follow-up. When one observer spots something unusual, alerts go out to the network requesting confirmation observations from other locations. This distributed approach catches transient phenomena that single observer programs might miss. The learning curve can be steep, but experienced amateurs produce data quality approaching professional standards. Careful calibration, multiple reference stars, and statistical analysis of measurement uncertainties transform backyard observations into scientifically rigorous datasets. Many amateur astronomers have decades of experience and understand observational techniques as thoroughly as professional researchers. Some amateurs specialize in specific contributions. Photometrists focus on precise brightness measurements. Astrometrists prioritize exact position determinations. Spectroscopists extract low-resolution spectra, showing major emission features. Each specialty adds unique value to the overall campaign. The amateur contribution represents astronomy's democratic nature. Meaningful observations do not require million-dollar facilities or institutional affiliations. Clear skies, decent equipment, careful technique, and dedication produce data that advances human understanding of the cosmos. 3. iAtlas belongs to everyone willing to point a telescope skyward and measure what they see. In approximately 3 weeks, 3 iAtlas will disappear from Earth's view. Not because it is departing, but because it is arriving at the most critical moment of its solar system passage. Perihelion will occur on the far side of the Sun from Earth's perspective. The geometry results from pure orbital mechanics, not intentional evasion. When 3 iAtlas reaches its closest approach to our star in late November 2025, the Sun itself will stand between the object and Earth-based observers. Solar glare extending millions of kilometers beyond the Sun's visible disk will render the comet completely unobservable from our planet. The blackout period will last roughly 6 to 8 weeks, depending on how close to the Sun observers are willing to point their instruments. Telescopes cannot safely observe regions too near the solar disk without risking damage from concentrated sunlight. Even specialized coronagraphs designed for solar observations have limits on how close they can look to the blinding disk. 3. iAtlas will pass through this forbidden zone during exactly the time when activity should reach maximum intensity. This timing represents one of the most frustrating aspects of the entire observation campaign. Months of monitoring building toward the perihelion climax, then forced blindness during the main event. It is like watching a thriller movie that cuts to black just before the resolution. The physics driving 3 iAtlas transformation will operate at peak efficiency, while Earth-based astronomers can only wait and wonder. The far side geometry does provide one scientific benefit. It tests whether the object exhibits any unexpected behavior when unobserved from Earth. Conspiracy theories suggesting intentional timing ignore that orbital mechanics was established by observations months before perihelion. The trajectory follows laws of gravity with no room for course corrections or evasive maneuvers. 3. Eye-Atlas goes where physics sends it. Ground-based observers will maintain watch up until the final days before solar conjunction, that astronomical term for alignment with the Sun. Images and spectra collected in mid-November will capture the last Earth-based views before the blackout begins. Those observations will show 3i Atlas at near maximum activity, providing baseline data for comparison with post-perihelion emergence. The weighting will test patience across the astronomical community. 6 weeks without direct observations of the most interesting interstellar visitor ever detected. No brightness measurements, no spectroscopy, no morphological monitoring, just Parker Solar Probe maintaining its lonely vigil from the solar vantage point, and Mars orbiters catching their brief glimpse during the November 3rd encounter. Then, the long wait until 3i Atlas emerges from behind the Sun and reveals what perihelion passage has done to it. Computer models are converging on what should happen when 3i Atlas reaches perihelion. And the predictions are staggering. Surface temperatures on the Sun-facing hemisphere will climb to approximately 300 degrees Kelvin, according to thermal models accounting for solar flux, sublimation cooling, and heat conduction into subsurface layers. That temperature, roughly 27 degrees Celsius, sounds almost pleasant by Earth standards. But in the vacuum of space, with no atmosphere to moderate heat transfer, it represents conditions hot enough to drive explosive ice sublimation. Gas production rates should peak near 400 kilograms per second at perihelion based on extrapolations from current activity trends. That represents more than double the current output measured in late October. Every second, roughly the mass of a grand piano worth of ice will transform into gas and stream away from the nucleus. Over the course of a day at peak activity, 3i Atlas will shed approximately 35 million kilograms. The dust production should scale similarly, potentially reaching 300 kilograms per second if the dust-to-gas ratio remains near current values. This creates a cloud of particles that scatters sunlight intensely, making the comet potentially visible to naked eye observers despite its distance. Brightness predictions suggest 3i Atlas could reach 6th or 7th magnitude at peak, just barely visible from dark sky locations for observers who know exactly where to look. Water vapor will dominate the outgassing composition at perihelion. Carbon dioxide, which drove early activity when the object was farther from the Sun, will continue sublimating, but become a minor component compared to water. The spectroscopic signature should shift dramatically as water emission lines overwhelm other molecular features. Jet activity will intensify with multiple active regions, potentially firing simultaneously. The rotation period may become clearly visible in rapid brightness variations as concentrated jets sweep across Earth's viewing direction every 11 hours. The inner coma could develop complex structure with spirals and shells created by the rotating jet pattern. Thermal stress will reach maximum levels not at perihelion itself, but during the rapid warming phase in the days immediately before closest approach. This is when fragmentation becomes most likely if the nucleus cannot withstand the the forces generated by differential expansion between ice and rock components. The predictions remain uncertain because comet behavior near perihelion often includes surprises. Unexpected outbursts, sudden brightness changes, or structural failures can occur without warning. Models provide best estimates based on current understanding, but 3I Atlas has already demonstrated its capacity for defying expectations. In 3 weeks, reality will test these predictions. The universe cares nothing for our models. The question astronomers dare not ask, too loudly, echoes through every observation. Will 3I Atlas survive perihelion intact? History offers sobering lessons. Comet Ikeya-Seki in 1965 grazed the Sun at just 460,000 kilometers above the surface, well inside the orbit of Mercury. It survived, but fragmented into multiple pieces that separated along its orbital path. Comet Lovejoy in 2011 passed even closer, just 140,000 kilometers from the solar surface, skimming through the corona itself. Against all expectations, it emerged intact, though severely battered by the experience. 3I Atlas will pass nowhere near that close. Its perihelion distance of roughly 0.9 astronomical units keeps it well outside even Mercury's orbit. The thermal environment will be intense, but not the apocalyptic heating that sun-grazing comets endure. By rights, survival should be straightforward for an object of such apparently enormous mass. Yet uncertainty persists because we still do not know for certain how massive 3I Atlas actually is. If the 33 trillion kilogram estimate proves accurate, the structural integrity should be more than sufficient. An object that size has enough gravitational self-attraction and bulk strength to resist fragmentation even under substantial thermal stress. The forces trying to tear it apart would be overwhelmed by the forces holding it together. But if the mass estimates are wrong, if some unrecognized factor makes 3I Atlas less massive than calculations suggest, then survival becomes questionable. A smaller, weaker nucleus might not withstand the temperature gradients and expansion stresses that peak during rapid perihelion warming. Fractures could propagate through the interior. Gas pressure might build beneath surface layers until explosive release tears chunks away from the main body. The rotation rate factors into survival calculations. Spinning at 11.3-hour period creates centrifugal forces at the equator that partially counteract gravitational cohesion. For a weak, loosely bound nucleus, rotation could provide the final push needed to separate fragments already stressed by thermal effects. The equatorial regions experience the highest rotational forces and might shed material preferentially. Tidal forces from solar gravity remain modest at 3I Atlas perihelion distance. The Sun's gravitational pull varies only slightly between the near and far sides of the nucleus at this distance, creating negligible stretching forces. Tidal disruption destroyed comet Shoemaker-Levy 9 when it passed too close to Jupiter, but 3I Atlas faces no comparable threat from solar tides. The survival question will be answered definitively in late November. Either 3I Atlas emerges intact, or it does not. No amount of modelling can predict with certainty what actually happens when theory meets reality at perihelion. The calendar shows early January 2026, and telescopes around the world are pointed toward the morning sky, where 3I Atlas should be emerging from its solar conjunction blackout. The first recovery observations will be challenging. The object remains close to the Sun in angular separation, visible only during twilight hours before sunrise when the sky is brightening. Observers must balance between waiting long enough for the comet to rise above the horizon and starting early enough that dawn twilight has not washed out the faint coma against the bright sky background. Recovery teams have calculated precise positions where 3I Atlas should appear based on orbital predictions. These predictions assume the object survived perihelion intact and continued following gravitational trajectory without fragmentation or unexpected accelerations. The first detection will confirm those assumptions or reveal that something changed during the unobserved perihelion passage. Initial images will answer the most pressing question immediately. Is 3I Atlas still a single object, or has it fragmented into multiple pieces? If fragmentation occurred, the morning sky should show several distinct condensations, where previously only one existed. Each fragment would follow slightly different orbits, spreading along the original trajectory like beads on a string. Brightness measurements from early recovery observations will indicate whether activity remains high after perihelion or has declined as the object moves away from peak solar heating. Models predict that outgassing should decrease as temperatures drop, but the exact rate depends on thermal inertia and how deep the heat wave penetrated into subsurface layers. Some comets show extended high activity after perihelion as stored heat continues driving sublimation. Morphological changes will be immediately obvious if they occurred. Has the antitail structure persisted or evolved? Are new jets active that were dormant before perihelion? Has the overall coma appearance changed dramatically? Comparing post-perihelion images with pre-perihelion observations from November will reveal what the solar heating did to the nuclear structure and activity patterns. Spectroscopy must wait for better observing geometry as 3I Atlas separates further from the Sun in the sky. Those crucial chemical measurements will show whether composition changed, whether new volatiles from deep interior layers have become exposed, or whether the chemistry remains similar to pre-perihelion observations. The emergence represents a moment of revelation. 6 weeks of waiting, 6 weeks of wondering, 6 weeks of speculation, all resolve into direct observations that will show definitively what perihelion passage did to this mysterious interstellar visitor. The telescopes are ready. The observers are waiting. 3I Atlas is about to reveal its secrets. The most critical measurements of the entire 3I Atlas observation campaign are happening right now in early January 2026, and they will determine whether months of mass estimates and theoretical speculation were correct. Post-perihelion astrometry provides the definitive test of non-gravitational acceleration. If the intense outgassing at perihelion finally produced measurable rocket forces, the trajectory should deviate from purely gravitational predictions. The deviation would be small, perhaps measured in arcseconds over weeks of observation. But precision astrometry can detect such subtle shifts. Every position measurement matters because they accumulate into a trajectory solution that either matches gravitational models or shows systematic residuals indicating additional forces. The physics is straightforward. At perihelion, 3I Atlas experienced its highest temperatures and most vigorous sublimation. Gas production rates potentially reached 400 kilograms per second or more. That represents enormous momentum transfer over hours and days of peak activity. Even an extremely massive nucleus should feel some recoil from such intense outgassing, unless the mass estimates were too conservative, and the object is even larger than 33 trillion kilograms. Observatories worldwide are measuring positions with milliarc-second precision, tracking 3I Atlas against background stars as it continues outbound from perihelion. The Minor Planet Center compiles these measurements continuously, updating orbital solutions daily as new data arrives. Analysts watch the residuals, those differences between observed positions and predicted positions based on gravitational models alone. So far, through early January, the residuals remain stubbornly consistent with zero non-gravitational acceleration. The object continues following a purely gravitational trajectory within measurement uncertainties. This is both remarkable and deeply puzzling. How can a comet that produced such vigorous activity at perihelion show no measurable orbital response to its own outgassing? 3 possibilities remain viable. First, 3I Atlas truly is extraordinarily massive, heavy enough that even peak perihelion outgassing produced recoil forces too small to detect with current measurement precision. This explanation supports the 33 trillion kilogram estimate and suggests the object might be even larger than preliminary calculations indicated. Second, the outgassing occurred in geometrically balanced patterns that cancelled momentum transfer. If jets fired in opposing directions with matched intensities, the net force could sum to nearly zero, despite substantial total gas production. This requires remarkable symmetry, but remains physically plausible. Third, something about the gas dynamics or momentum transfer efficiency differs from standard comet physics assumptions. Perhaps dust dominates the mass loss and carries momentum differently than gas phase sublimation. Perhaps the gas escapes through porous surface structures that redirect momentum in unexpected ways. Perhaps some exotic physical process operates that current models do not account for. The acceleration test will continue for months as 3I Atlas moves farther from the Sun and observing conditions improve. Every additional position measurement tightens constraints on possible non-gravitational forces. If acceleration remains undetectable through mid-2026, the mass estimates gain credibility. If subtle deviations finally emerge, the entire theoretical framework will require revision. Right now, 3I Atlas maintains its reputation as the silent giant, shrugging off its own breath with the indifference of a mountain-ignoring wind. NASA faces one of the most consequential decisions in interstellar object astronomy: whether to redirect Juno spacecraft toward a close encounter with 3I Atlas during its March 2026 passage near Jupiter. The technical analysis is complete. Engineers have confirmed that Juno possesses sufficient fuel reserves to execute the trajectory change required for intercept. The maneuver would use Jupiter's gravitational field in an Oberth effect assist, firing engines at closest approach to the planet where orbital velocities reach maximum, and every kilogram of propellant delivers maximum momentum change. The physics works. The fuel exists. The capability is real. But capability does not equal decision. Redirecting Juno means abandoning its extended mission, studying Jupiter's magnetic field, gravitational anomalies, and atmospheric dynamics. Years of planned observations would be sacrificed for a single close encounter with an interstellar visitor. The trade-off pits guaranteed Jupiter science against potentially revolutionary but uncertain 3I Atlas discoveries. Congressional pressure continues building. Multiple representatives have sent letters urging NASA to pursue the encounter opportunity. Public interest remains intense, with social media campaigns advocating for the mission redirect. The political dimension adds complexity to what should be a purely scientific decision based on merit and resource allocation. The scientific case for redirect has strengthened following perihelion observations. 3. I-Atlas survived intact, emerged with continued high activity, and maintains its anomalous lack of non-gravitational acceleration. These characteristics make it the most scientifically interesting interstellar visitor detected to date, potentially justifying the sacrifice of Juno's Jupiter mission. In situ sampling would answer questions impossible to address through remote observations. Direct analysis of coma dust and gas would determine exact chemical compositions, isotopic ratios, and organic molecule inventories. Magnetic field measurements would reveal interaction with the solar wind. Close-range imaging might resolve surface features on the nucleus itself. The data quality would exceed anything ground-based or space-based telescopes can achieve from Earth distances. The timeline forces decision urgency. Trajectory modifications require weeks of planning and execution. If NASA approves the redirect, commands must be uploaded to Juno soon to allow time for the complex orbital maneuvers needed to reach intercept geometry by mid-March. Opposition argues that sacrificing a functioning planetary mission for a single flyby sets dangerous precedent. What happens when the next interesting object appears? Do we redirect every available spacecraft toward whatever seems novel at the moment, abandoning carefully planned science programs? The decision will come within days. NASA leadership weighs scientific merit, technical feasibility, cost-benefit analysis, and programmatic implications. 3. I-Atlas waits, unaware that human institutions debate whether to send a spacecraft to meet it. Vera Rubin Observatory has begun its systematic survey of the southern sky, and the first results are rewriting everything astronomers thought they knew about interstellar visitors. Early data from the Legacy Survey of Space and Time, collected during commissioning operations in late 2025 and early 2026, has detected 3 additional interstellar objects, 3 new visitors in just 4 months of partial operations. The discovery rate exceeds even optimistic predictions by factors of 2 or 3. More remarkably, 2 of these newly detected objects show characteristics similar to 3I Atlas. Preliminary astrometry suggests substantial mass based on active outgassing without corresponding non-gravitational acceleration. The pattern is repeating. What seemed like an extraordinary anomaly when 3I Atlas was discovered may actually represent a common class of interstellar visitor that previous surveys simply missed. The size distribution emerging from early LSST data challenges theoretical predictions. Models anticipated that small objects should vastly outnumber large ones, following steep power law distributions, where each doubling of size produces roughly 8 times fewer objects. Instead, the preliminary sample shows an unexpectedly flat distribution, with massive visitors appearing almost as frequently as smaller ones. This population revelation forces fundamental questions about ejection mechanisms and interstellar debris reservoirs. If massive objects are common, stellar systems must eject them more efficiently than current theories predict. Perhaps close stellar encounters in dense star-forming regions scatter large bodies more effectively than planet-to-planet gravitational interactions. Perhaps something about the ejection process preferentially launches heavy objects while destroying or retaining smaller debris. Survivorship bias may also play a role. The journey through interstellar space spans millions of years under constant bombardment by cosmic rays and occasional collisions with interstellar dust. Small objects might erode away or fragment during transit, removing them from the arriving population. Only robust, massive bodies survive the crossing intact, biasing detected populations toward the large end, regardless of initial size distributions. The capture and planet seeding hypothesis gains credibility if massive interstellar objects prove common. Young stellar systems swimming in a sea of kilometer-scale debris could capture enough material to significantly influence planet formation outcomes. What seemed like speculative theory when based on a single unusual object becomes plausible mechanism when multiple examples appear regularly. Detection efficiency must be carefully analyzed before drawing firm conclusions. LSST finds objects based on brightness, and massive active comets appear brighter than small dormant ones. The apparent abundance of large visitors might reflect observational bias rather than true population characteristics. Correcting for detection efficiency requires sophisticated modeling of survey capabilities and visibility windows. The population picture will clarify as LSST accumulates years of data. The revelation has only just begun. The peer-reviewed paper finally appeared in February 2026, and the refined mass estimates for 3I Atlas carry tighter error bars that change the conversation entirely. After months of preliminary calculations and preprint circulation, the formal publication presents analysis of over 7,000 positional measurements spanning 9 months of observations. The statistical rigor is unprecedented for an interstellar object. Multiple independent analysis teams have verified the orbital solution and non-gravitational acceleration limits using different methodologies. The results converge. The lower limit on nucleus mass sits at 28 trillion kilograms, with an upper limit near 42 trillion kilograms. The best estimate remains 33 trillion kilograms, unchanged from preliminary calculations, but the uncertainty range has narrowed substantially. Combined with improved constraints on gas production rates from JWST spectroscopy, the corresponding nucleus diameter estimates range from 4.8 to 6.2 kilometers. This is genuinely enormous by interstellar visitor standards. The publication confirms what months of preliminary data suggested. 3I Atlas represents a new class of object, massive enough that outgassing produces negligible orbital perturbations, even during peak perihelion activity. The silent giant designation has graduated from speculation to established characterization. The nickel without iron mystery receives partial resolution in the same publication. Laboratory experiments recreating low-temperature photodesorption conditions demonstrate that certain nickel-bearing organic compounds release metal atoms preferentially under ultraviolet irradiation, while iron-bearing compounds remain stable. The selective chemistry likely reflects unusual formation conditions rather than exotic physics. 3I Atlas formed in an environment cold enough for these specific compounds to condense, compounds that do not form in warmer solar system comet birth regions. Chemical modeling, combining JWST spectroscopy with laboratory data, converges on formation temperatures below 25 degrees Kelvin. This places 3I Atlas origin in the extreme outer reaches of its parent stellar system, possibly beyond 100 astronomical units from the parent star. Only at such distances would temperatures drop low enough for the observed chemistry to develop. The deuterium enrichment and carbon isotope ratios support this frigid formation scenario. Multiple independent chemical clocks all point toward the same conclusion. 3I Atlas is a messenger from the coldest regions of an alien stellar system, carrying frozen chemistry that has remained largely unaltered for billions of years. Theoretical convergence does not mean every mystery is solved. The population statistics remain puzzling. The anti-tail structure still defies complete explanation. But the core questions about mass, chemistry, and origin have moved from speculation to evidence-based understanding. The theoretical framework supporting 3I Atlas characterization now rests on peer-reviewed foundations rather than preliminary calculations. Science is working as it should, gradually converting mysteries into knowledge. If Vera Rubin Observatory continues detecting massive interstellar objects at current rates, the planet seeding hypothesis transforms from speculative idea into testable mechanism, with profound implications for understanding planetary system formation throughout the galaxy. The mathematics are becoming compelling. If one massive interstellar visitor passes through the inner solar system every few months, as early LSST data suggests, then young stellar systems embedded in dense star-forming regions experience vastly higher encounter rates. A protoplanetary disk lasting 5 million years in a typical stellar nursery could capture dozens or hundreds of kilometer-scale objects during the critical window when giant planets form. Each captured object represents a ready-made planetary core, bypassing the meter-size barrier that plagues traditional core accretion theory. Instead of slowly accumulating from dust grains, through pebbles, to boulders, to planetesimals, the captured interstellar visitor provides instant scaffolding for rapid gas accretion. A 5-kilometer nucleus captured into a circular orbit within a massive protoplanetary disk could grow to Jupiter mass in less than 1 million years. The chemical implications extend beyond simple mass considerations. Interstellar objects carry compositions reflecting their birth environments in different stellar systems. A captured visitor formed in a carbon-rich disk around a low-mass star would inject different chemistry than locally formed material. This mixing of material from multiple stellar sources could explain some of the compositional diversity observed in exoplanet atmospheres. Population synthesis models, incorporating interstellar seeding, predict correlations between stellar mass and giant planet occurrence that match observational trends better than models without seeding. Massive stars form in denser clusters where interstellar encounter rates peak. They also possess deeper gravitational potential wells that capture passing objects more efficiently. Both effects favor giant planet formation around massive stars, exactly what exoplanet surveys observe. The skeptics raise valid concerns. Captured objects must survive tidal disruption during the capture process. They must avoid subsequent ejection through gravitational interactions with other forming planets. They must migrate to disk regions where gas densities support rapid accretion. Each step introduces failure modes that could prevent successful seeding, even if capture occurs frequently. Testing the hypothesis requires better constraints on interstellar object size distributions, chemical compositions, and velocities relative to stellar systems. LSST will provide size distribution data within years. Chemical characterization requires spectroscopy of multiple visitors. velocity distributions emerge from orbital analysis of large samples. The seeding mechanism may operate alongside traditional planet formation rather than replacing it. Both pathways could contribute, depending on stellar environment and disk properties. 3. I-Atlas and its massive companions might be revealing a previously unrecognized channel for planetary system assembly. 3. I-Atlas is leaving, accelerating back towards the interstellar medium from which it emerged, and astronomers are watching it fade into the cosmic distance, with instruments tracking every stage of its departure. By March 2026, the object has passed Jupiter's orbit outbound and continues gaining distance from the Sun. Activity is declining as solar heating weakens with increasing distance. Gas production rates have dropped to roughly 100 kilograms per second, half the peak perihelion values. The coma contracts as sublimation slows. The brightness fades steadily as both intrinsic activity and viewing geometry become less favorable. Observing campaigns continue despite the dimming. Every additional data point refines our understanding of how interstellar visitors behave throughout their complete solar system passage. The outbound observations complement inbound data, testing whether activity evolution shows symmetry or reveals differences between approach and departure phases. The final astrometric measurements will extend through late 2026 as 3I Atlas becomes too faint for all but the largest telescopes to detect. These positions will provide the definitive trajectory determination, confirming whether any subtle non-gravitational forces emerged during the months since perihelion. So far, the object maintains its reputation, showing purely gravitational motion within measurement precision. What we learned from 3I Atlas will shape interstellar object astronomy for decades. The observation protocols developed during this campaign provide templates for future visitors. The theoretical frameworks, challenged and refined by its anomalous properties, advance understanding of comet physics and interstellar debris populations. The global coordination demonstrated during months of intensive monitoring establishes precedent for international collaboration on transient astronomical phenomena. 3I Atlas will spend the next several years crossing the outer solar system before finally achieving escape velocity and returning to interstellar space. It carries with it slightly less mass than when it arrived, having shed perhaps 0.1% of its total mass through sublimation. The frozen chemistry from an alien stellar system departs mostly intact, barely touched by its brief encounter with our Sun. The silent giant returns to silence. The sky has not finished revealing its secrets. Even as 3I Atlas fades from view, Vera Rubin Observatory continues its nightly survey, and new interstellar visitors appear regularly in the data stream. By mid-2026, LSST has detected 7 confirmed interstellar objects since beginning full operations. The discovery rate suggests dozens will be catalogued annually once the survey reaches full efficiency. What seemed impossible just years ago, finding visitors from other stellar systems, has become routine observational astronomy. The era of interstellar object science has truly begun. Each new detection adds to our understanding of the galactic debris field. Size distributions are taking shape. Chemical diversity is emerging through spectroscopic follow-up. Orbital characteristics reveal information about ejection velocities and source populations. The statistical samples needed for robust population analysis are finally accumulating. 3I Atlas remains the most thoroughly studied interstellar visitor to date.
Its massive nature, unusual chemistry, and complete observation coverage from discovery through perihelion to outbound departure provide a benchmark against which future visitors will be compared. It established that massive objects exist in the interstellar medium and forced recognition that our theoretical frameworks needed updating. The questions it raised continue driving research. Why do massive objects appear as frequently as small ones? What ejection mechanisms launch kilometre-scale bodies efficiently? How common is the silent giant phenomenon where activity produces no measurable acceleration? Does planet seeding operate throughout the galaxy? Future instruments will provide answers current technology cannot. Extremely large telescopes coming online in the late 2020s will enable detailed spectroscopy of faint, distant visitors. Space-based infrared observatories will map thermal properties and chemical inventories. Perhaps eventually, a dedicated spacecraft mission will rendezvous with an interstellar object, providing the in-situ measurements that remote observations can never match. The watch continues because the universe keeps sending messengers. 3i Atlas was extraordinary, but it will not be the last surprise the space between stars delivers to our doorstep. We are listening. We are watching. We are ready.